Ladies and gentlemen, please welcome Charles Norton, Deputy Chief Technologist at JPL, to the stage.
Oh, hello. Hello, everyone. Thank you so much for coming to the William H. Pickering Lecture. So the origins of JPL actually date back to the 1930s, prior to the formation of NASA, when Caltech students and faculty performed pioneering work in rocket propulsion in the dry canyon north of the Rose Bowl, where JPL currently stands. And through various programs sponsored by the U.S. Army's Ordnance Corps through the 1940s, rocket motors and missile technologies were advanced, leading JPL to propose with Wernher von Braun's team a satellite launch in 1954 for the upcoming International Geophysical Year. But sadly, that proposal was rejected. But nevertheless, given the pioneering success of the Soviet launches of Sputnik and Sputnik 2 and challenges with the U.S. Navy's response from the Vanguard project, JPL and the Army Ballistic Missile Agency successfully launched Explorer 1 on January 31st, 1958, carrying James Van Allen's Geiger counter that discovered the Earth's radiation belts. And later on that year, on December 3rd, 1958, JPL's responsibilities were transferred to the newly formed NASA to lead robotic scientific exploration of the solar system and beyond. And although Theodore von Karman, Frank Molina, and Louis Dunn preceded William H. Pickering as JPL directors from 1938 to 1954, this lecture series today celebrates William Pickering, the former JPL director, to honor his initiation and leadership of America's robotic space program from Explorer 1 in 1958 through development of the Viking orbiters and the Voyager outer planet missions and interstellar missions. So with that, I'm just so pleased and excited to introduce you to Dr. Bonnie Buratti of JPL. She's a deputy project scientist for the Europa Clipper mission. Bonnie is a senior research scientist, principal, and fellow at JPL. She's an expert on planetary surfaces, and she's held leadership roles on several NASA flight projects, including Cassini, the mission to Saturn, and the New Horizons mission to Pluto. Bonnie is also a recipient of the Carl Sagan Medal for Excellence in Public Communication and the Gerald P. Kuiper Prize for Outstanding Lifetime Achievement in the field of planetary science. She's an elected fellow of the American Geophysical Union and the American Astronomical Society, and author of over 250 papers, including the popular book, Worlds Fantastic, Worlds Familiar by Cambridge. So please join me in welcoming Bonnie to the Ascend stage for Europa Clipper, first NASA mission to an ocean world.
Thank you so much, Charles. Well, things are pretty exciting now at JPL because we're getting ready to launch. We already have our spacecraft at the Cape, and we're going to launch hopefully on October 10th. That's when our launch period opens. So I'm going to tell you about this first mission to an ocean world, first detailed mission. Let's start at the beginning with Galileo. He's the one that discovered the four Galileo, they're now called the Galilean moons, Io, Europa, Ganymede, and Callisto. And there on the left, you see a note from his, one page from his book, Sidereus Nuncius, that shows the position of the four moons around Jupiter, which led to the demise of the geocentric view of our solar system, that the Earth is the center and not the sun. Now, one of the things that, as a communicator of science, I like to do is dispel scientific misconceptions. And I'm going to dispel the first one. You probably learned in school, as I did, that Copernicus was the person that really came up with the idea of the heliocentric solar system. But it was actually the early Greeks, people like Aristophanes, that guy that measured the size of the Earth to 50 miles, Aristarchus, and Anaximander. They were Greek empiricists, experimentalists, who also knew that the sun was at the center of the solar system. And another little personal story here. when I was working on Cassini, we had a little meeting up at the Pope's summer residence. We had our meeting in Rome, and Guy Consolmagno, who's now the director of the Vatican Observatory, invited a few Cassini scientists up there just to kind of see some stuff. And one of the things I saw and touched with my hands was the Vatican's copy of Sidereus Nuncius. And as I was touching that, I realized this is the same copy that was touched by Galileo's inquisitors. Quite an emotional experience. Okay, so here's just a picture taken by Galileo's spacecraft of the 4 moons, and above that is Galileo's little sketch. Okay, moving on to some of the early spacecraft observations. There was Pioneer 10, and then Voyager in 1979, Voyager 1 and 2. And I did my thesis on Europa, and that one there on the middle, that's Voyager 1 went by, and we saw this strange appearance like a cracked egg, and we were wondering what it was. It was kind of suspenseful. And, well, this is what it is. There are all these marks of active geology on Europa. There's an image on the left of the entire disk of this fascinating moon, and there on the right, you see all these, they're called lineae, striations, and you can see that there's episodic activity on Europa, because some of those lineae go over some of the older features caused by a previous event. Okay, let's see some of the things that Galileo took. These are the so-called chaos terrain that show what's known as rafting. Geologists, I'm an astronomer, so some of my geology descriptions are naive, but there are these kind of iceberg-like features from this ice shell of Europa kind of floating on the surface. That's the chaos terrain. And there are not many craters on Europa. Now, here is my second dispel of scientific misinformation. You probably learned in school, as I did, that the reason the Earth doesn't have any craters is because they all get burned up in the atmosphere. That's wrong. If a meteoroid is big enough to make a crater, it's going to get through the atmosphere. So the reason that we don't have any craters to speak of on the Earth is because they've all been eroded away. So geologists use crater counts to tell how old a surface is. So from that, we know that Europa is pretty recent, about 100 million years old, which is young geologically speaking. Europa is about 4.6 billion years old, as old as the solar system. Okay, but there are a couple craters, a few craters. There's Puil, the biggest crater, and it's recent. There are these mysterious features called lenticulae. We don't quite know what they are, but we think that they have something to do with this fascinating ocean underneath. I'll get to that. So here's just kind of a collection of some of the other interesting pictures that Galileo took. There are some more craters there that have some kind of deposit around them. There are features, there are color images that show the composition changes. Quite a mysterious object. So what causes this active geology? Well, it turns out it's tidal heating. The orbit of Europa is elliptical, so the tidal force from Jupiter is closer when it is closer to Jupiter. And that flexing, that mechanical heat gets dissipated, mechanical energy gets dissipated as heat energy. And that's what causes this heating. And we think that that is what also causes what we know, we're pretty certain there's a liquid ocean, a subsurface ocean on Europa. Now, how do we know that? Well, here is the magnetic field of Jupiter. Now, Jupiter orbits or rotates on its axis about every 10 hours. And the orbit of Europa around Jupiter is about 3.5 days. So that great magnetic field of Europa kind of slams into the back of Europa. The great magnetic field of Jupiter slams into the back of Europa. And remember from your physics class Faraday's law, if you have a magnetic field going through a conducting medium, which is water, it's going to induce a magnetic field. And that's what we observed. That's what Galileo observed on Europa. That's why we're pretty certain that it's got this liquid Ocean. We think it's about 20 kilometers underneath this ice shell on the surface. And there's also a core, a rocky, possibly iron core in the center. Okay, so what does this look like? This is an artist's conception. There's a icy crust of about 20, 30 kilometers. Then there's this ocean underneath, and we think it's a salty ocean, which is key, about maybe 80 kilometers. So it has, we think, on Europa has all the ingredients for life. It has water, life as we know it needs water. It has food, essential elements, molecules with carbon, hydrogen, oxygen, nitrogen, and some kind of chemical or some type of energy. And on Europa, we think there may be two types of energy. The heat from below, you can see there's a crust there that's kind of warm, causing these smokers, more on that later, these thermal vents. But we also think that there's some chemical energy. If it's salt, there are ions, positive and negative ions, and that causes almost like a battery there, some type of energy that is conducive to a habitable environment where life can form and thrive. Okay, and it's also been stable for hundreds of millions of years. So just a little bit more history here. So when I was in graduate school, it was believed that life formed in the shallow seas of the Earth, where these warm seas got zapped by lightning, and then some miracle occurred and amino acids formed, and then life, another miracle somehow formed from that amino acid. So this was this so-called Urey-Miller experiment. Urey was the supervisor of Stanley Miller, the University of Chicago, who did experiments like that, where you take what then was thought to be similar to the composition of the early Earth's atmosphere and zapped it with this ultraviolet light, mimicking the sun and or lightning. And amino acids did in fact form. Now, I got my PhD at Cornell University, and I was one of Carl Sagan's students, and Bishan Kari had a lab where he was replicating these experiments. And all this goo, which Carl Sagan termed intractable polymers, were formed on the edges of these flasks that Bishan had in his lab. It was quite neat being there in the thick of things. But we've kind of abandoned that model for the origin of life. There's another theory, which it's widely accepted, but I wouldn't say it's totally accepted. And that is that primitive life on the Earth formed in these thermal vents in the deep oceans. And why do we know that? Because if you look at these thermal vents, there's one here on the right, hydrothermal vent. The bacterial life that's down there, it's very primitive. The most primitive life on Earth did not, for example, need oxygen. They were anaerobic. So these primitive bacteria that thrive at these thermal vents, they're the same creatures that exist at the trunk of the tree of life. We think that all life on Earth formed from these unicellular, simple organisms. It's not 100% accepted. My friend and colleague Penny Boston, for example, thinks that life originated in caves, which is another interesting habitable environment that might exist on Mars, for example. Anyway, let's get on to life on Europa, the search for life on Europa. We're not looking for life, we're just searching for a habitable environment. Okay, but I just want to show this fanciful. This is one of my favorite images of these possible thermal vents on Europa. This was actually an official NASA image showing Europa's ocean as a habitable environment. And it really is fanciful because you see a little device here in the back going through this crust, which is 20 kilometers or more deep. And even on Earth, it's just in the last few years that we were able to drill through. The Russians drilled through some of the ice crust in Antarctica and got through to this Lake Vostok underneath. That was a technological breakthrough and did in fact find primitive bacteria and other forms of life there. But it's really a kind of a visionary image there of searching for habitable environments and possible life in the deep ocean of Europa. Okay, so let's talk about Europa itself. First of all, it has more water, liquid water, than Earth, we believe. There is Earth, and there's the amount of water. And if you go to that image of Europa on the right, which is, and these are to scale, Europa is a little bit smaller than the moon. It has, we think, about twice as much liquid water in this subsurface ocean. And again, liquid water is what we need for life as we know it. Now Mars is a different story. Mars did have liquid water on its surface in the past. In fact, it almost certainly had standing water and possibly an ocean around the northern hemisphere. And many scientists believe that life originated on this early, more Earth-like Mars. And then the water escaped from the planet because it has less gravity than the Earth. And this life, this primitive life, bacterial life, kind of hunkered down in the subcrust, in the crust of Mars. That's one model. So NASA is also searching for habitable environments and possible life on Mars at the same time. Okay, so let's talk about the Europa Clipper mission science, the main goals of it. We are going to characterize the ice shell and the ocean, the depth of the ocean, and its top and its bottom. We would like to do that. And we'd also like to know how salty it is, characterize the composition, the salinity of the ocean. We're also going to look for compositional markers, focusing on things that are signs of a habitable environment, such as organic molecules, things like polycyclic aromatic hydrocarbons, anything that's made out of carbon chains, oxygen and nitrogen. We're also going to search for evaporate deposits, things that may have suggested water came onto the surface and sublimated. So we're looking for that as well. And then, of course, we're going to look at the geology, characterize its activity and geologic episodes and what actually caused it to be Europa. And then the other thing we're going to look for is activity. There is some evidence, there are 5 or 6 incidents of what look like geologic activity currently occurring on Europa. A little bit more on that later. I think actually my next slide shows an example of that. But a 5th thing we're doing is reconnaissance, looking at Europa for a possible landed mission. We were working on it at JPL, but it got canceled. But in the future, we'd like to put a lander on Europa. Okay, so evidence for activity. There are about 5 or 6 incidences. There's one actually from the 1970s where 2 observers in Hawaii saw some heat markers of something on Europa. And they claimed in their paper that they published in the journal Icarus that their data was unassailable, and they saw the thermal signal go up about a factor of 5. But it's kind of tucked in their paper. The Hubble Space Telescope actually showed 2 events that occurred of activity on Europa. And here's data from one of them where it shows this emanation from the OH molecule from water, a possible plume on Europa there in the lower left. You see it about 7 o'clock. The James Webb Space Telescope looked quite closely for evidence of activity on Europa, but did not find any. Okay, there's another piece of evidence for a plume on Europa. And I've actually quoted, if you're really interested in the details, I've quoted from the article there on the right. It's in Science, it's a journal, and that's taken right out of the article that says exactly what happened, but I'll kind of put it in simpler terms, that the Galileo spacecraft, and by the way, this data was analyzed a couple decades after the actual data, which really highlights the importance of archiving data. We now archive, NASA has been archiving all its data for decades, and anyone, I mean, this is the heritage of the American people. You can go and look at that data yourself. But now even journals are starting to insist that authors archive their data, the original data and the reduced data, to just make it useful and easy for other people to access it. But this data was reanalyzed, and what the investigators saw was that the magnetic field, those little blue lines or the magnetic field lines, looked like they kind of draped over what was claimed to be a plume. So that's another evidence, and it was in the area where the Hubble Space Telescope saw these plumes. So that's another piece of evidence, but it's not 100% accepted, but it is one thing we're going to be searching for during the mission. Okay, so here are the instruments. There will be a test on this, just kidding. Okay, at the top are the remote sensing instruments, and at the bottom are what are now called in situ instruments, which means in place, but I actually don't like that term because to me in situ means you're actually there on the surface, so I still call them fields and particles instruments. But we have kind of the classic instruments there at the top that NASA's flagship missions have. A flagship mission is like a Cadillac mission. It's a big mission that goes, in this case, to the outer solar system. The Mars rovers, some of them were more modest missions, but the current rovers, the latest rovers on Mars are also flagship missions. So here we have an ultraviolet spectrometer to look for, characterize the atmosphere and also to look for plumes and also the composition of the surface. We have what's known as the Europa Imaging System ICE, which is actually two cameras, a wide-angle one, which actually gives almost 50 degrees field of view, and then a more narrow-angle one for high-resolution imaging. We have the MISE, which is this infrared spectrometer, which is going to do most of the compositional mapping, looking for those evaporate deposits and organics. We have ETHEMIS, which is a thermal imager, which is going to be characterizing the heat balance on the moon, but also look for active plumes by looking for thermal hotspots. And then finally, we have this very innovative radar system called REASON, which I'll show you what it looks like. We're not using the disk of the high gain antenna. It has these other antennas which are attached to the solar panels. It's very innovative. And then we have the in situ, the fields and particles instruments that are going to look at the particles, the ions, the dust. And when scientists say dust, they also mean water, ice particles. There's a magnetometer. And finally, there's a plasma sensor. And finally, there is the gravity radio science experiment, which does use the the antennas that are on the spacecraft to understand the shape of Europa, the shape in its interior. Dead battery. Let's see, can people hear me now? I'll just talk into this. Okay, I'm okay. All right, so here is the actual spacecraft that shows you the position of the instruments. And what I want to focus on here is actually the solar panels. They are bigger than anything in deep space. They're not as big as the solar panels on the space station, but they are the biggest thing in deep space. Now, the last mission, Galileo, that went, well, actually, we have Juno, which is another spacecraft right now at Jupiter. But the last spacecraft that looked at Europa in detail was Galileo. That was powered by radioisotopes. But we have a solar panel, these solar panels on Europa Clipper. So there are the positions of the instruments. But those little things sticking out, there are actually 6 antennas sticking out from the solar panels. Those are the REASON ice-penetrating radar, which will look at, try to understand the depth of the ocean and how deep it is. Okay. Okay, so let's see. I think there's a little, there's a movie there, but I'm not sure how I can start it. Okay, there we go. Okay. These are where all the positions of the instruments are. And this is an interesting spacecraft in that we don't really have to move it to operate. It is going to make about 50 orbits around Europa. It's actually orbiting Jupiter and then sweeping in about 50 times to make these close passes by Europa. And the in situ instruments will be on the front of the spacecraft in the ram direction, basically scooping up particles, whereas all the remote sensing instruments will be looking down, nadir looking, and map the surface. So we don't have to do any of these complicated motions of the spacecraft like we did on Cassini. Okay, let's see. There we go. This just shows various instruments. And here are the flybys that we're making. It's a global web of flybys trying to cover the surface, go at different altitudes down as low as 35 kilometers, and we go out, much further than that, but trying to sample the atmosphere at different heights above the surface. That's our global web of flybys. Okay, so the size of the Europa Clipper spacecraft. Okay, let's start with SLS. There's a Statue of Liberty. I should have probably, and that's the one in New York City. Okay, not the one here. I should have maybe had some local cover, but I was wondering when I was driving in, I saw the Chrysler building, the fake Chrysler building, and the Chrysler building is actually copyrighted. Maybe it got out of copyrighted, but I was wondering, did they copyright that? I don't think the Statue of Liberty is copyrighted though. If it were, it'd be out of copyright anyway. So there's a bunch of railroad cars, 6 railroad cars. Okay, there's the Falcon X Heavy. This is the one that is going to launch us. Okay, we wanted to go on the SLS, but it didn't work out, so Falcon Heavy. There's Europa Clipper with its glorious solar panels, and there's the magnetometer sticking out, and there's a basketball court. So that's how big we are. Biggest spacecraft to ever go in, I believe it's the biggest spacecraft ever to go into deep space. Okay, so here we are in the clean room, the high bay at JPL, while it's in ATLO, assembly, tests, launch operations, and there are a couple instruments we can see. It's at the Cape now. It's continuing ATLO at the Cape. Okay, now the solar panels, the solar arrays were built by Airbus. And here they are in Holland, getting their final kind of cleaning and packaging up and everything like that. And here we are in what's known as shake and bake, back at JPL. So on the right, there's our spacecraft finally being sewn up. As you all probably know, you have to put these shields on it, and they're actually sewn by hand around the spacecraft as protective devices. And there we are up on the little mesa behind JPL that has a facility that will put the spacecraft in the same temperature and solar conditions that are expected in space, as well as kind of shake it to simulate a launch. And we made it through that kind of with a charm. There were a couple technical issues, but I won't go into the details. I think the funniest one was that since this hadn't been used for a while, is a couple of the light bulbs that simulate the sun had burned out. I think that wasn't the worst thing, but I won't go into the worst thing. Okay, so here is our launch and trajectory. There are a few obligatory slides you have to show whenever you're talking about a space mission. This is one of them. The other one is the launch scenario, the launch movie, but I don't have that yet. Hopefully in a few months we'll have that. So here is, as I said, the launch period opens on October 10th from Cape Canaveral, and then only about 4.5 months after launch, we get a gravity assist at Mars. And through lots of arm twisting, we are going to get a few calibrations at Mars. We're going to turn on the radar instrument, which we can't really do an end-to-end test at Earth. So that's going to be on at Mars. And there are a couple of heritage instruments in orbit now, Marsis and Sherrod, that are like Reason. They're also ice-penetrating radars that studied the polar caps of Mars. So we're going to get that data and test for reason. And eThemis, which is the thermal instrument, is also going to get some images of Mars. There's also a heritage instrument on the Odyssey spacecraft called Themis. We have eThemis. So it's going to go by Mars and loop around in the inner solar system. As you all probably know, it does this to build up enough momentum to get to Jupiter. We can't go on a direct launch. We could have with SLS, but it just wasn't ready. Okay, so then we go by Earth. I actually can't read this from here, but it's about a little over a year later, and then on to Jupiter in a more than 5-year journey. So that's our mission plan. And as I said, there are about 50 close flybys of Europa while we are orbiting Jupiter. The reason we orbit Jupiter and go out on this wide orbit is because the environment, the fields and particle environment, the radiation environment in the inner part of the system where Europa is very harsh. So we have to spend most of our time out away from that harsh environment. Okay, so I do want to spend a little bit of time. I want to finish up in a couple minutes so we have some time for questions, but I did want to mention this really interesting thing we did. As you know, NASA likes to send little mementos out into space, and it started with that the controversial gold record that was on the Voyager spacecraft, which one of my colleagues, of course that was done while I was in actually it was launched while I was just finishing up my undergraduate work, and one of my student colleagues there said, that spacecraft is going to be decayed by neutrino bombardment before any aliens see that plaque. As you know, neutrinos hardly interact with matter at all, so it's just going to be out there forever. But anyway, we did have a similar type of campaign for Europa Clipper, where we got 2.6 million signatures, put it on a little chip, and there's this plaque, which I'll be showing you in the next slide, that has that microchip installed. And we also had this poem. Let me go to the next. That campaign was called Message in a Bottle. Let me go on to this next one here. Whoops, I have to go back. Okay, so here's our plaque. And it has a poem that was written just for us by Ada Limon, who is the Poet Laureate of the U.S. She's also a MacArthur Fellow, the Genius Grant. We debuted this poem at the Library of Congress, I think it was back in April. And it was really almost a spiritual event. I'm going to be reading the poem actually in about a minute. So that's on one side. We also have the Drake equation, which is an equation that Frank Drake, who's also one of my teachers, one of my professors at Cornell, and he just recently died. He's just larger than life person, along with Carl Sagan and so many other people of his generation. He developed the Drake equation, which gives the probability of habitable environment, habitable Earth-like planet, life arising, intelligent life, and then technology and intelligent civilization. That's a Drake equation at the top. And then on the lower left is Professor Greeley from Arizona State University, who was the project scientist is Bob Pappalardo. I'm the deputy project scientist. That was his thesis advisor, and he died before his time, so there is his image there. We wanted to have some ashes from Greeley and Drake put on the spacecraft, but NASA nixed it because there is a policy, and I think this is good policy, not to do that sort of thing. When I was working on New Horizons, we did manage to get some ashes, a little container of Clyde Tombaug's ashes. He was the discoverer of Pluto, so we got some of his ashes on the first mission that went to Pluto. But quite honestly, it was done on the sly. There are only, I think, 2 people on the mission. Alan Stern, who was the principal investigator, and maybe 1 or 2 engineers that put this little vial of ashes on the spacecraft. I was a co-investigator on the mission, and I didn't know about it until after launch. So if you do want to do these things, you have to do it on the sly. You can't get permission. So, no. And the other thing that's so funny, there's a little kind of commemorative sentence on the where Clyde's ashes are. And I also had the privilege of meeting Clyde Tombaugh. He came to JPL for a seminar around 1984. This was before he passed away, because I met him. He's a character, and he's a punster. So on this little container, it says, "Here interned are the ashes of Clyde Tombaugh." Well, interned, of course, means to be in jail. Interred is the proper word. And at first I thought, well, this is a misspelling, this is a typo, but then I realized it's his last pun. So he was really another larger-than-life character. And then, so that's on the inside of the plaque. On the outside of the plaque, there are the waveforms of the word for water in over 100 languages. Okay, now I'm going to read the poem, and I can't do it the justice that Ada would give it. I had the privilege of meeting her. She came to the clean room at JPL, the high bay. But I think there's a movie here. I think I can get it started. So I have to, let me see if I can get, there's a movie on this one, but I think I might have, I can't. It was working, but do I have to do something, some tech thing? Is that, maybe that's it. Oh, is it going? Okay, all right. Let me read the poem. Arching under the night sky. Oh, the title is In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky. The whale song, the songbird singing, its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water, each drop of rain, each rivulet, each pulse, each vein. O second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark. Thank you so much. And here's some ways you can get involved. I think there's time for some questions. Thank you.
Well, thank you very much, Bonnie. Here's a mic for the Q&A. We're sorry that your lavalier went out.
Yeah, it was a battery thing. Okay, great.
Oh, wonderful. Thank you so much. So there are a couple of questions that have come in. One is, if the ice recycles itself, would you be able to find traces of life within ice samples on or near the surface of Europa?
If we were able to get samples, that would be a possibility. That's kind of what we're trying to do on Mars. And you're probably familiar with the Martian meteorite. There are meteorites on the Earth that come from Mars, and there was that interesting feature. It was like a little, well, it was a possible bacterial form of life from Mars that showed evidence, it was controversial, of life on the surface of Mars. Yes, if we had a lander, we could be looking for similar types of things.
Very good. Another question, will Clipper take any data about the other Jovian moons?
Right now, it's not in the plan, but the duty of the project science staff is to push for these types of observations. We are making flybys. There's a flyby of Ganymede 6 months before orbit insertion, and we'll definitely be looking at Ganymede, and there are additional flybys of Ganymede and also of Callisto don't think Io. Io is so embedded in that energetic particle environment that it's kind of iffy. But yes, Ganymede and Callisto, we will fight to get those observations, and we will win. Have in the past.
Yeah, and I recall I noticed in your talk the images of the trajectory for the encounters with Europa, and it's on a very highly elliptical orbit.
Absolutely, yeah, and it's elliptical, so we get away from that energy environment. But Ganymede and Callisto are further out, so it's not as dangerous, especially Callisto.
Okay, another question is, what is the status of Clipper's electronics and their tolerance for radiation?
Yeah, so there's a couple ways to answer that. The first one is that we have a lot of the electronics in a vault, protected from the radiation. And the other thing that we did was space harden all the electronic parts. You may have read in the newspaper that there were some transistors on board that did not meet the specification they're supposed to. And right now we are analyzing that problem. We are understanding how well they respond to radiation and looking at mitigations, and we still expect to make the launch. There isn't any, these problems do come up late on in the ATLO process, and we're working them and still hope to make launch.
Absolutely. Given the ocean at Europa is expected to be salty, do we expect to find chemical signatures of life there similar to that on Earth?
Okay, that's a really good question. Well, in the last few years, actually the last few decades, there have been astrobiologists have shown us that there's life existing on practically every environment on the Earth. They exist miles down in the Earth's crust. They exist, I believe there are even organisms that can exist in boiling water. There are organisms that can exist in, pHDs of like 2. And there are organisms that can exist in salty water as well. So I don't think if there's a salty environment there that it would be any detriment to life. And life just seems to evolve in whatever environment it's thrust into through Darwinian evolution.
Very good. When you earlier compared Mars with Europa, did you have any sense as to where past signs of life may be more likely?
That's a really good question, and I don't have an answer for that. And the reason I don't have an answer is that science is always based on the accumulation of data and facts. And right now, we know so little about life's origin and its persistence, and we don't have enough data to answer that. I think they're both good places to look. They're both places where we follow the water. That is kind of the mantra of astrobiology, of looking for life outside our own world. And there was massive water on standing water and probably oceans on Mars, and a lot of that water is now underneath the surface, and life could have hunkered down. And we believe on Europa there is, and we're trying to seek a habitable environment where primitive life could form in a way similar to the way it did on the Earth, but we don't have any data yet. So therefore, I don't have a preference for either one.
Very good. I think we have time for two last questions. What could we learn and reuse on this Europa Clipper mission for other icy moon missions or locales like Enceladus?
Yeah, there are actually a bunch of ocean worlds in our own solar system. Enceladus is one of them, and this is the smaller moon of Saturn, and it has actually been studied by Cassini. It's got a plume, it's got a subsurface ocean, it's definitely active. And then there are Pluto may also have a subsurface ocean. Ganymede probably does. There is an asteroid Ceres. It's actually a dwarf planet. It's in that same category as Pluto. It may also have a subsurface pool at least, because from ground-based observations, the OH molecule was observed above the surface, and it looks like there are bright icy deposits around this crater called Akator. So what we are learning from the Europa Clipper, first of all, how to map out the existence and extent of the ocean in the interior, And then what are the kinds of chemical markers we have to look for on the surface that will be applied to future missions to ocean worlds.
And finally, what happens at the end of the mission? Surely you won't crash it into Europa due to planetary protection reasons.
Yes, we do have an end game. As you mentioned, because of planetary protection, we cannot crash into Europa. Our current plan is to end the life of the mission at Ganymede, because this is thought to be much less likely, although there is evidence for a subsurface ocean on Ganymede too, but it's less likely to harbor life. It's not currently active. It's not as stable, the ocean. So our end game is to impact Ganymede.
Oh, well, thank you so much, Bonnie. I think on behalf of all of us, we're so pleased you could share your knowledge and experience with us and to educate us on this important mission. You know, on behalf of AIAA, we have a certificate for you. Perhaps I'll take your microphone here for photographic purposes. To thank you on behalf of giving the 2024 Pickering Lecture. Oh, thank you. Okay. Thank you so much, Bonnie.
Thank you. Thank you.
Thank you all very much.